Assalamualaikum and hi everyone. At the end of this lesson of 2.1 Bohr's atomic model, you should be able to describe the Bohr's atomic postulates, explain the existence of electron energy levels in an atom and calculate the energy of electron, differentiate between line spectrum and continuous spectrum, and we will see example of calculation involving the Rydberg equation for Lyman, Balmer, Paschen, bracket, and Van series. So please stay with me until the end of the lesson and enjoy your learning. Before we discuss more on Bohr's atomic model, so let us see the historical development of atomic theory over the centuries. We will start with Billiard-Ball model by John Dalton. John Dalton proposed that all matter is composed of tiny atoms. So matter, whether it is in the form of elements, molecules or compounds, so all of them are actually made up of tiny atoms. And he also proposed that these tiny atoms are indestructible, cannot be created, cannot be divided into smaller particles or destroyed. And he also found out that the shape of the atom is in this spherical shape. But scientists cannot agree with his theory because he did claim that atoms cannot be divided into smaller particles. But in real, after that, scientists have found out that atoms can be divided into smaller particles. That is called as subatomic particles. We have learned this one in chapter 1. So atom has subatomic particles and they are proton, electron, and neutron. And later, J.J. Thomson proposed Plum pudding model in 1904, and he is the one who discovers electron. He won his Nobel Prize for this discovery. He proposed that electrons were positioned uniformly throughout the positively atom, just like in pudding. And why it is so called plum pudding model? Because he imagined that the electron as plum, which is scattered around the positively atom. Okay, so atom is like the pudding and the electron is just like the plum. So the plum or the electron positionally scattered throughout the entire space of the atom, just like in pudding. So in this model, J.J. Thomson has claimed that he found the electron and also the atom as having positive charge, and also the location of the electron scattered just like the plum in the pudding. Later in 1911, Rutherford discovers positively charged nucleus. And he also states that mass of atom is concentrated at the nucleus. This is because he has discovered the proton inside the nucleus. And nucleus is located or situated at the center of the atom. He also proposed that atom is actually made up of empty space. So most of the space in an atom is actually the empty space. But unfortunately, he cannot explain the electron movement in orbit. Later, Bohr proposed Bohr's atomic model in 1913, and it is also known as Planetary Model. In this model, Bohr states that electron travels in defined circular orbit and energy levels around a nucleus. So in this model, Bohr has improvised what cannot be discovered by Rutherford. Bohr atomic model, however, has some limitations. His theory can explain well for hydrogen atom or hydrogen-like species. But this theory or model cannot be extended to multi-electron species. So that is one of the limitations of Bohr atomic model. In 1926, Erwin Schrödinger has come out with a new theory known as quantum mechanical model. In this model, he has improvised what have been done by Bohr in his model. So according to this model, He proposed that electrons move in wave, not in specific orbit like what have Bohr proposed in his theory before. So Schrödinger states that there is no specific orbit in an atom, but there is probability subshell or place to find the electron in an atom. So according to Schrödinger, there is no specific orbit like what Bohr had found in his theory. It is actually a probability space in this atom where we could find the electron. And also the other thing is he also mentions that electron move in wave, not exactly in this circular orbit. And also in this theory, in his model, he also come out with this term electron cloud. In this video, we will focus more on these two latest theories that are Bohr's atomic model and quantum mechanical model. And you will see on how this quantum mechanical model by Schrödinger will overtake the Bohr's atomic model. And atomic model after these years will use this quantum mechanical model. Bohr's atomic model that is proposed by Niels Bohr in 1913 refined the Rutherford atomic model in explaining the movement of electrons around the nucleus. So previously, we have discussed the weakness of Rutherford atomic model, whereby Rutherford cannot explain more on the movement of electron in the nucleus. In Bohr's atomic model, he discovered that electrons circling a central nucleus that contains positively charged protons in fixed orbit. And he also discovered that orbits can only occur at specifically permitted levels only, according to the energy levels of the electron. And his theory can explain successfully the lines in the hydrogen spectrum. So Bohr's theory can be used to study for hydrogen spectrum or hydrogen-like species only. Here we are going to discuss a few postulates of Bohr's atomic model. For the first postulate, it is said that electron of hydrogen atom moves in circular orbit around the nucleus. So these are the orbits as proposed by the Bohr theory. In moving the orbit, the electron does not radiate or absorb any energy. So electron will keep moving in its own orbit without giving out or accepting any form of energy. In the second postulate, the energy of a hydrogen atom is quantized, meaning that each orbit has a fixed amount of energy. Electron moving in permitted orbit can have only a certain amount of energy. We can have electron orbiting the nucleus at n1 and also electron can orbiting the nucleus at n2, but the energy of electron that orbiting the nucleus at n1 will not equals to the energy of electron that orbiting the nucleus at n2. So that is mean by quantized. Energy is quantized. Each orbit or permitted energy level is represented by using an integer known as principal quantum number. So in order to label the orbit in Bohr atomic model, we will use integer number. Okay, for example, n1, n2, n3 until n infinity. And you cannot use any fractions number or decimal points to label the orbit. And the orbit can also known as the stationary states and shells. These are the orbits that proposed in Bohr's atomic model. According to postulate 3, each orbit is represented by an integer known as principal quantum number n. So in this case, we can label this orbit by using an integer. Let's say for this first orbit, we can label it as n1. second orbit as N2, third orbit as N3, and the fourth orbit as N4. So please bear in mind the value to be used in order to label this orbit could only be in integer form. It cannot be in fractions and it cannot be in decimal points. So these integers are the permitted energy levels in Bohr's atomic model. Electron can only be on these specific energy levels or orbit. Electron cannot be in between this energy level. Electron cannot be between these energy levels. It must be on the specific permitted energy levels only. So this is one of the postulates in Bohr's atomic model.
Second postulate states that the energy of electron in a specific energy level is quantized. It means that the energy of electron when it is located at N1 will not equals to the energy of electron when it is located at N2. This is because the value of energy of each orbit is exclusive and it is not identical to other energy levels or orbit. Non-orbit or energy levels having the same value of energy.
So to know the energy of electron in a given orbit, we can calculate the energy by using this formula. En equals to negative RH times 1 over n squared, whereby the En is actually the energy at specific energy level. RH is the Rydberg constant in joules, and n is the principal quantum number. So let's say you are going to find the energy of electron when it's circling at N1. So you have to substitute this N value with 1 and this N also with 1. Okay, by doing that, you will be able to find the energy of electron at first orbit.
Hence, by using this formula, you will be able to find the value of energy when electron is located at these specific energy levels. In order to calculate energy of electron when it is located at N1, you can simply substitute the value of N1 into this formula. So the formula now will become E1 equals to negative RH 1 over 1 squared. So by doing that calculation, you will get the value of energy at first energy level is this value. And you can also find the energy of electron at the other energy levels by using the same formula. Okay, it's just that you have to substitute this n value with the required energy level that you are going to find its energy. So if you are about to find the energy of electron at N2, so you may simply substitute these two values into this formula, becoming E2 equals to negative RH times 1 over 2 squared. And you will get the energy of electron at N2 is this value. And energy of electron at third energy level will has this value. From these values E1, E2, E3 until E6, we can see that each orbit has their own energy values. And these values are exclusive to the respective orbit or energy level. None of the orbit has the same value of energy. This is what we call as energy of electron at specific orbit is quantized. Electron that is nearest to the nucleus will have the lowest energy, that is more negative. An electron that is farther from the nucleus has higher energy, that is less negative. Energy is zero if electron is located infinitely far from the nucleus, which is at n infinity. So where is the n infinity? So n infinity can be assumed to be at the outermost orbital or orbit. Okay, di orbit yang paling luar. So in order to calculate the energy of orbital or the energy of electron at infinity orbital, you may substitute this n with infinity. So E infinity equals to negative RH 1 over infinity squared. You will get this energy value will be 0. Okay, why the energy is 0 when n is infinity? Because at this position, electron will experience no more attraction with the nucleus. But why the electron that nearest to the nucleus has the lowest energy or the more negative energy? This is because electron at this position experience the most attraction force with the nucleus, okay, due to the closest position to the nucleus.
So now let's see the difference in calculation to find the energy of electron in joules per atom and in kilojoules per mole. In this example, you are going to find the energy of electron but in two different units. The first one is in joules per atom and the second one in kilojoules per mole. In the first example, you are going to calculate the energy of an electron when it occupies N1 in joules per atom. In finding this answer, you have to use the previous formula.
By using the above En formula, the unit in the final answer will be in joule per atom.
In this example, you are going to calculate the energy of an electron when it occupies N3 but in kilojoules per mole. So for the first step, you have to use the same formula here to find the energy of electron in joules per atom. And to get the answer in kilojoules per mole, so what you have to do is you have to times with Avogadro constant. By multiply this answer in joule per atom with Avogadro constant, you will get your answer in kilojoule per mole. And not to forget, from this answer, please divide with 1000 to get your answer in kilojoule from joules. From these two examples of calculation, I hope you can see the difference in calculation of energy of an electron in joules per atom and kilojoules per mole.
At ordinary conditions, electron of hydrogen atom has the lowest possible energy and occupies the ground state n equals to 1. So at ordinary conditions, electron will be at this ground state, which is n equals to 1. Ground state is the lowest energy level and the most stable state of atom, that is at room temperature. When energy is supplied to the electron at the ground state will absorb the energy supplied and move from ground state, which is lower energy level, to the excited state. So this is the ground state, that is lower energy level. After this electron has absorbed certain amount of energy, it will get excited to this higher energy level. And this higher energy level is also known as excited state. This process is called absorption or excitation process. Excited state is the higher energy level, and it happens when sufficient energy is supplied to an atom absorbs the energy. So in order for this electron to get excited to the excited state or higher energy level, this electron must absorb certain amount of energy, so the value of delta E will be in positive. So how we can calculate the value of delta E? Delta E is the energy difference between the high energy level to this low energy level. Since for the excitation, we will start with this lower energy level to higher energy level. So this lower energy level, we can label it as N1, Ni, and the higher energy level up here can be labeled as Nf. So from the value of Ni here, you can find the initial energy, and from the value of Nf, you can find the final energy, which is Ef. So the delta E will be the difference of energy from Ef minus Ei, whereby this Ef is energy of electron when it is at, in this case, N4, and Ei is the energy of electron when it is at N1. Electron at the excited state is highly unstable, so after some time it will fall back to lower energy level and release specific amount of energy. So delta E, the sign will be in negative, showing that energy has been released from this reaction. So this process is called emission process. In emission, electron is moving from high energy level to low energy level, from excited state to ground state. So we can label this high or excited state as an initial for emission. And since this electron is moving to low energy level here, so this low energy level can be labeled as Nf. So from the Ni, you will be able to find its energy Ei, which is initial energy value. And from this Nf, you can also find its final energy. So in order to find the value of this energy difference, it can be calculated by final energy minus initial energy, where the final energy is when the electron is at N1 and the initial energy is when the electron is at N4. So by doing this calculation, you will definitely get the value of delta E in negative.
The negative in delta E value is consistent with the energy released from the emission reaction. Both excitation or absorption and emission process involving electron transition.
Okay, pergerakan elektron, electronic transition. For excitation, the electronic transition occurs when the electron moves from low energy level to high energy level. For example, from N1 to N4. So during this transition, electron will absorb certain amount of energy and the delta E value will be in positive. Meanwhile, in emission process, the electronic transition involved in this process will be from N4 to N1, for example, N4 to N1. Okay, so during this transition, electron will fall from high energy level to lower energy level and radiation will be emitted. And this radiation will has certain amount of energy delta E and with the respective wavelength and frequency. So for this electronic transition, whether it is in excitation or emission, you will be able to find their delta E value. In absorption or excitation, delta E will be in positive, and in emission, delta E will be in negative. To calculate energy of electronic transition, for example, in this emission process, you must be able to identify its final and initial energy states. So in this emission process, this is the higher energy state, and this is the lower energy state or energy level. So since we are talking about emission process, electron will fall from this higher energy level to this lower energy level. So this higher energy level can be labeled as Ni, initial energy level. And from this Ni, you can find the value of its energy, which is Ei. And then electron falls to lower energy level here. So lower energy level will be our final destination. So this will be NF. So from this NF, you can also calculate its EF. So how to calculate the value of EI and EF? You can simply use this formula. So by these two formulas, to find the delta E, you have to minus EF and EI. So to simplify all this calculation, we can simply use this formula. Delta E equals to RH times 1 over Ni squared minus 1 over Nf squared. So in order to put our Ni and Nf value, you must be able to identify which one is initial energy level and final energy level according to our process. As in this emission process, since the movement of electron is from higher energy level to lower energy level, so this higher or excited energy level will be labeled as Ni, and this ground state or lower energy level will be labeled as Nf. So to find the delta E for that emission process, you can substitute this Ni as 3 and N final as 2. Okay, where the RH is the Rydberg constant. So by solving this calculation, you will get your answer in negative. Can we calculate the energy or delta E for electronic transition for absorption? The answer is yes. So for example, let's say we have electron at second energy level get excited to this higher energy level. So in this case, according to the movement of electron moves from this low energy level to this high energy level or excited states. So according to the movement of the electron, we can identify the energy level at N2 as N initial and energy level at N3 as N final according to the electronic transition in absorption or excitation. So from the NF, you should be able to find its final energy value, and for NR, you should be able to find its initial energy value. So to get the energy difference delta E for this electronic transition in excitation, you can get the value from this mathematical operation, E final minus E initial. And you can also, using a simplified formula we have done, okay, at the bottom here, which is delta E equals to RH 1 over Ni squared minus 1 over Nf squared. So according to this electron movement in excitation, this is our initial energy level, and this is our final energy level. So by substituting the values Ni as 2 and N final as 3, so by solving this mathematical operation, you will get the value of delta E in positive. As the conclusion, it is very important for you to identify which one is N initial and N final, whether in excitation or emission process. Because by knowing these two energy level conditions, you will be able to find the delta E for each excitation and emission process. And please remember, the delta E for excitation will be in positive,
and delta E for emission should be in negative. And in this example as well, we can see that since the electronic transition for excitation and emission involving the same energy level, which is from N2 to N3 for excitation and N3 to N2 for emission, we should expect the magnitude value of delta E in excitation and emission will be the same. Okay, so what I mean is the energy delta E for excitation maybe is 50 kilojoule, and in the emission, its delta E value will be in negative 50 kilojoule. So why these two processes has the same magnitude value? It is because they involve the same electronic transition from 2 to 3 and 3 to 2. Okay, but what the main difference between them is only the sign of the delta E. Okay, positive is for excitation and negative is for emission.
To recap, in excitation, specific amount of energy is absorbed. Electron is excited from lower energy level to the higher energy level. So this will be the Ni for excitation and Nf of the excitation. So during the process, energy has been absorbed. So the delta E will be in positive. And for the emission, electrons from high energy level will fall to the lower energy level. So for the emission, Ni is the higher energy level and Nf is the lower energy level. So the process of this electron falling back to lower energy level will release energy, and the amount of energy will be in negative, showing that energy has been released from the reaction. And from the delta E value, we can further calculate the frequency and wavelength, because all energy or specific energy will have their own respective frequency and wavelength. So in order to calculate frequency and wavelength, we can use this formula. Delta E equals to HV equals to HC over lambda, whereby the H is the Planck constant and C is the speed of light.
Calculate the energy in joules of a photon having frequency of 7 times 10 power of 15 Hz. So in this case, you are needed to find the value of energy, and we have the value of frequency in the question in unit Hz. So 1 unit Hertz equals to 1 per second. So to find the answer of energy, we will use this formula. Delta E equals to H frequency. If a photon has this amount of energy, what its wavelength in meters? So to find this answer, you can use this formula. Delta E equals to Hc over lambda. Lambda is the wavelength. So rearrange this formula. We will have lambda equals to Hc over delta E.
Thank you for watching, everyone. I hope this video could help to enhance your understanding in chemistry. Have fun in your learning, and remember, chemistry is easy and fun.